let me open this meeting, this SETSI workshop, on the occasion of Sakae's retirement. So just a few things about this workshop. Originally, we wanted to have this last year. Sakae retired last year, just a year ago, at the end of March 2020. And we wanted to have this workshop basically in March last year. But then this was canceled because of Corona. I mean, there is nothing we could do about that. And then we first thought, well, let's shift this and this will soon be over and at some point we will have it. But that did not work out well, and we are still in Corona, and still there is no, there are still travel restrictions around the world. So in the end, we decided to have it online. Just a couple of months ago, we made this decision, and that's how we got into this online workshop. So it's really 1 year late. Let me very briefly say something about Sakae. I mean, this is a very informal workshop, so what I will say will also be very informal. Sakae, as all of you know, is a very active researcher in set theory and with very broad research interests. Set theory, then of course also Boolean algebras, forcing, and so on, and also in mathematical logic in general, and also in towards philosophy and other areas. He got his degree, or all his degrees, from the Free University in Berlin, and actually stayed in Germany for almost 20 years, mostly at the Free University, from 79 to 97, first as a student and then later as an assistant professor. And then he came back to Japan in 1997, and he first was for 4 years at Kitami Institute of Technology in Hokkaido. So that was till 2001. And then for 8 years, from 2001 to 2009 at Chubu University, that's close to Nagoya. It's a small private university. And then finally at Kobe University from 2009 onwards till his retirement in 2020, last year. He has many research publications, and he's still very active, and there are lots of, if you look at his page, there are lots of preprints and planned projects and so on. As I said, this is a very informal introduction, so I don't want to say much about his research. Just let me say something about his very recent work. Most of his I mean, he has older work on many other topics, but most of his recent work is on reflection in set theory. Reflection is really an important and central theme, and he has worked a lot on this. So he has a series of papers on Fyodor-type reflection principles, and then more recently, there is his work on strong downward Löwenheim-Skolem theorems for stationary logics, and I think there is much more to come. So, I hope he will stay active and prove many more theorems and have many more papers. I think that's all I want to say, and let me now, let's start. And Sakae will talk, the title of his talk is Monte Carlo Strategies for Guessing Games and Takeuti's Reflection Axiom. Yoroshiku onegai shimasu.
Thank you very much for a nice introduction. This conference is sort of embarrassing for me because I'm connected with it in connection with my retirement. But when I mentioned this embarrassment in another Zoom seminar, Jan van Mille, I think that was Jan who said that I shouldn't feel embarrassed with my retirement or something like that. But actually, there's a good reason to be embarrassed a little bit about the retirement, especially in Japan, because many people or many mathematicians at least, become inactive very early. So that means if you are a retired person, then the expectation is that you are out of the business of mathematics. And but for me, retirement means just retirement from these stupid professor meetings and business with entrance examination and these kind of things, right? So, I have to explain that I'm willing to remain active in mathematics each time when I mention my retirement, and this is already quite a bit embarrassing. So, but in any case, I hope I can prove my activity in mathematics with this talk. So let me begin with the talk. So I like to talk about two types of axioms. Takeuti mentioned in 1999. Professor Takeuti died a couple of years ago, but at that time he still published many articles in Japanese monthly journal, which is for hobby mathematicians and mathematics students mainly, but also for researchers and rather broad audience. And in that article of 1999, he talked about two axioms or two possible axioms as extension of the usual extent of axiom set theory. One of them was an axiom proposed by Søren Ries. And another one is a very old axiom of him, which is he called, I think, reflection axiom or something like that, in a 1971 paper. So I'd like to talk about these two axioms, and I'd like to try to connect them in the context of large continuum. Large continuum means that a continuum is okay. There are several aspects of largeness of continuum, but you'll see in the talk what I mean. Now, so this is the first page of his article in Japanese. One of the axioms is that of Ries, and it is formulated in this way. So let I be the unit interval, and N the idea of null sets over the unit interval. Then we consider the following guessing game between two players, player 1 and player 2. This is just one single step game where player 1 guesses a real in the interval, but simultaneously player 2 guesses a countable subset of the unit interval. And player 2 wins if the guess of the player 1 is included in his countable guess. Now, we consider the following kind of strategy, kind of statistical strategy or something like that, which is a sequence of countable sets indexed by elements of the interval. And it is called a Monte Carlo strategy. This is just my naming, but I think the naming suggests the content of the intention of the idea. So this is a Monte Carlo strategy. If for any move of the player 1, the set of indices where A is not included in AR is in the null set. is in the ideal of null set. So this means if player 2 randomly choose an index and the set countable set attached to the index, then it will win the game with probability 1. Okay, I said it just because I think that my game is played by 2 robots, just to avoid any misunderstanding in sexist kind of situations, right? So this is my player 2. But in any case, Srenri's thought that it is impossible that player 2 has such a strategy in the game because countable sets are, in fact, too weak compared with the continuum. So he formulated his feeling in the axiom and said that there is no Monte Carlo strategy for player 2 in the game as in the previous slide. So it sounds quite natural, but it has several interesting consequences. And one of them is that continuum hypothesis is refuted by this axiom. And this is quite easy to see. So suppose continuum hypothesis holds. So I have to show that in the case there is a Monte Carlo strategy, but if I take a filtration of the interval and assign elements of the interval 1 to 1 to each real, then this sequence is a Monte Carlo strategy because for any real, there's some index alpha, and from that on, all the countable sets in the filtration contain the real. That means the error set is just countable. So in particular, measure 0. So this Monte Carlo strategy is a strategy in a very strong sense, in that the error set is not only measure 0 but countable. So CH does not hold under this axiom. Now, this is not Monte Carlo strategy, but Monte Carlo street. I don't know. I shouldn't do this kind of joke, but yeah. This, actually, in the world, there are several Monte Carlo streets, and this is somewhere in Canada. I chose this place because it looks so empty and sad, but I don't know. In any case, I can consider this idea with game in a more in a broader setting. So instead of considering countable sets and null ideal, I consider 2 arbitrary ideals over unit interval. And I define the principle RJI as the statement that there is a sequence AR of element of J such that for any real A from the unit interval, the error set, I mean the set of all indices where A is not contained in AR, guessing element, is in the ideal I. So we can also consider corresponding game between players 1 and 2, and consider the sequence as a strategy for a player 2. So I will call such a sequence Monte Carlo strategy for for the pair I and J. So when I write less than kappa to denote the ideal of sets of size less than kappa, and n the new ideal, then Rees' axiom is not other than the statement that R less than Aleph1 n does not hold. And it is easy to see the monotony of the principles. If I and I prime, J and J prime are all ideals, and if I is subset of I prime and J is a subset of J prime, then RJI implies I of J prime, I prime. Because if I have a Monte Carlo strategy for J and I, then it is also a Monte Carlo strategy for J prime and I prime. Now, I don't know if Lajos still remember this, but he proved the following almost 20 years ago, I guess, when he was in Kitami. Namely, with this notation, R less than Aleph1, less than Aleph1 is equivalent to the continuum hypothesis. This is a quite nice characterization of a continuum hypothesis. There are many nice characterization, but this is also quite nice, I think. And the proof goes as follows. One of the direction is already proved with the idea of filtration of interval. I can prove this direction, or actually theorem 1 and the monotonicity I just mentioned will imply this direction. And for the other direction, we can argue in this way. So assume that CH does not hold. And so this is the contraposition. I like to prove the contraposition. And toward a contradiction, I suppose that the principle R less than Aleph1 holds. That means there is a sequence which is the Monte Carlo strategy for ideals of countable sets. Then let XC less than Aleph1 be a one-to-one sequence of elements of I. And for each XC, let XC be the error set for this sequence AR. This is countable. So if I take the union of all XCs, then I'll get a set of size less than or equal to Aleph1, which is by assumption strictly less than continuum. So there is some real R, which is outside this set S. But if I look at AR, then AR contains XC because it does, R is not in the set. AR contains XC, and this happens for all C less than omega 1, and this is a contradiction because I assume that all AR are countable because it was Monte Carlo strategy for countable sets, and this is a contradiction. So the same proofs shows that R less than kappa is just equivalent to the statement that the continuum is less than or equal to kappa. Now, actually, Yoshinobu-san also proved a theorem in this context almost 20 years ago. Namely, Rij is equivalent to the following statement. It's kind of a contraposition of it, which is which states that there is a sequence EA, A in I, in I. So in the statement of RJI, we had a sequence in J, but now we're talking about sequence in I, with the property that for any subset of unit interval not in J, if I take the union of EA from A for A from S, then it is always the whole unit interval. This is, okay. I think I have, yeah, I thought, yeah, I think it's a better idea not to go into the proof, but I can just show the slides of the proof. One direction is done in with this much argument, and the other direction is this much argument. It's not very complicated, but I just skipped the proof just because of the time. But if I have this characterization, then I can get easily several useful facts about this principle. First of all, Rij implies that covering number is less than or equal to uniformity of J. This can be seen in this equation. So if I have a set S, which is not in J, then I can find a covering of I of that much sets from I. So this shows this direction, and a little bit more argument, but easily we can also show that Rji implies covering number of J is less than or equal to uniformity of I. Yeah, I think just to be on the safer side, I also skipped the proof. It's not also quite easy, but I prefer to go to further claims. So as a corollary, we get for any kappa less than continuum, R less than kappa I implies that the covering number of I is less than or equal to kappa, which is in this case strictly less than continuum, and none of I is just continuum. This is because the covering number and uniformity of sets of cardinality less than kappa is kappa and continuum. So if we use this to and apply these corollaries, we'll get this inequality and inequality. We also have another quite trivial fact, namely, if uniformity of J and I are both continuum, then Rji holds automatically. This is just by the same kind of idea that I take a filtration of I, then it is a sequence of element of J. And if I define the guessing sequence, this Monte Carlo candidate of Monte Carlo strategy, just by one-to-one enumerating this sequence by reals in the unit interval, then this is actually Monte Carlo strategy for the pair Ij. So this proves that this cardinal value of cardinal invariance implies that this principle holds. Now, if we have this much, I mean, we can continue this and do all the standard, and answer all the standard questions of set theory of reals in this connection. But instead, I'd like to stop just by mentioning the consequence and Martin's axiom plus non-CH. So we know much about this principle and this combination of axioms. So first of all, Rees axiom and also the topological dual of Rees axiom holds under Martin's axiom plus non-CH. Here we need actually non-CH because non-CH is implied from Rees axiom. Moreover, we can also obtain easily that the corresponding negation of the principles for kappa, for all kappa less than 2 to Aleph naught. On the other hand, if I take ij from a null ideal, omega ideal, or actually much more similar ideals, then we have Rji. This is because under Martin's axiom plus non-CH, we have all cardinal invariants of null and mega ideal equals continuum. So I can use just this proportion 9 and to get this and for 1 and 2, because we need a small covering number to get R something. We get negation everywhere here. Yeah, so under Martin's axiom plus non-CH, things are quite clear. I mean, we can do much more things, but I just prefer to go to some sort of pseudo philosophical argument in connection to these things. Now, as I mentioned earlier, Søren Riis thought that this is the proof of negation of a continuum hypothesis, because having a Monte Carlo strategy is something very unnatural, or what he thought is unnatural. But if we argue in this way, then we can also look at, for example, Banach-Tarski theorem, which says that this is the GFC theorem, and axiom choice is the crucial point of the theorem. But this is about the finite partition of ball. And if you claim that existence of Monte Carlo strategy is something very unnatural, then this theorem is much more unnatural. I mean, because the object claimed to exist is sort of more physical, because it is, in any case, finite partition, right? Of course, it is a cheat, because it is not said that each component of the finite partition is surely not physically realizable. But in any case, Ries axiom as the proof of negation of continuum hypothesis is something very weird, because then we have to negate the axiom of choice first, just because of this comparison of degree of unnaturalness. still, I tend to claim that because this axiom and its dual are consequences of Martin's axiom, I could perhaps say that they support, I mean, it's not the reason, but support at least the combination Martin's axiom plus negation of CH. This is just a claim with big question mark and nothing more than that. But in any case, this consideration reminds me the following more mathematical, possibly more mathematical question, namely what we obtain if we restrict ourselves to definable sets, for example, projective sets, which should be Monte Carlo strategy. I mean, we only consider Monte Carlo strategy, which are definable in one sense or another. Because in the earlier arguments, several times well-ordering of the real was used in form of filtration of the reals. So perhaps this kind of restriction may make the question more interesting. Yeah, but with this much, I would rather like to move to the other axiom, namely Takeuti's reflection axiom. He proposed originally in let me see, 1971 paper, but then he reformulated actually in a quite different way in his 1999 article I mentioned earlier. And this is the axiom, which is something like the following. For any ordinal alpha 0, strictly bigger than omega 1, and for any subset of p omega, there is a transitive set omega m star such that alpha 0 is in m star. So it can be quite big, right? Because it's transitive. If alpha 0 is in m star, then alpha 0 is included in m star. But p omega is not included in m star. And the third condition is sort of weird. Okay, I'll explain why it is very weird. But in any way, this condition says that the structure M, together with unary predicate, which is interpreted as A intersection M star, and all these constants, alpha 0 and all alphas from omega 1, and of course the Ipson relation as the binary relation is equivalent to V, A, and all these constants, which are just the same thing. So these two structures should be elementary equivalent. Actually, Cohen also wrote a paper about a similar kind of axiom and mentioned them as Takeuti's axioms. And one of the axiom he discusses in his paper. By the way, this might be the very last set theoretic paper of Paul Cohen. Around 1975, I think 1974 or something like that, he moved to the study of Riemann conjecture. I think so. And then he never returned to set theory. So as far as I could see, this was the very last paper of him in set theory. But in that paper, he mentioned a slight weakening of the Takeuti's axiom I formulated here. as I have formulated here. Namely, he drops the parameter alpha 0, and it says practically the same things without this. Now, the significance of this kind of axioms is that they express certain kind of richness of the power set of omega. So it says that power set of omega is very rich, and so that it cannot be captured by all transitive models, where we consider these transitive models so strong that they reflect the full truth of the universe in the sense of elementary equivalence, and also these parameters from omega 1, and in case of the Takeuti's first Takeuti's 1999 axiom, he also fixes alpha 0 as the parameter. So in a sense, it expresses the richness of power set of omega. So in that sense, at least it is a very interesting axiom, but there is a problem with these axioms, namely they are inconsistent, at least in their original formulation, because of the theorem of undefinability of the truth by Tarski. So this can be seen in this way. So undefinability of the truth of Tarski is the, perhaps I don't need to explain to most of you what is this theorem, but just to be sure. So this is a theorem which holds for any concretely given theory in a language, in some language L, so that diagonal lemma can be formulated in this language, and it is true in T. So for such a theory T, of course, I assume that T is consistent. If T is consistent, then there is no formula he such that he defines the truth of in T, in the sense that phi, each sentence phi is equivalent to he of numeral of phi, good sentence of good recording of phi. So there's no such he, and this is a quite easy application of diagonal lemma. Now, if I consider Takeuti's axiom, then we have this situation here, or this one. In any case, let me see. In any case, if I formulate a sentence in the set theory, which says that there exists an M star, as in Takeuti's axiom, and this M star models phi. Because this is a set model, we can write a sentence as expressing this one, right? But this would be a truth definition. So this cannot be the case. Or if you could formulate this, then you've got a contradiction. We have to reformulate these axioms and take some weakenings of them to get something meaningful. So this is one big problem, but there's another problem, namely in these axioms, it is said that P omega is not in this mysterious model M star. And this is if M star satisfies enough set theory, then this is equivalent to saying that P omega is not the subset of omega star. So there is some real outside M star, but these axioms do not specify what kind of reals we can have outside M. So this is the problem about reals outside M star. Shouldn't be remain unmentioned at all. So I'd like to address to these two problems and give a certain kind of solution to them. First, to the consistency, I can formulate the version of the Cohen paper in this way, which is consistent. Or instead of saying elementary equivalent, I just consider each single formula. I mean, this is an axiom schema. So phi here is a metamathematical formula in an extended language with a new unary predicate. For each such formula, we have that for any subset of P omega, there's a transitive set M star such that, okay, so I formulate the axiom for each kappa. Kappa is an element of M star, but P omega is not an element of M star. And for all parameters, which are elements of kappa, we have this equivalence. So the structure M star with the interpretation of the unary predicate A intersection M star together with epsilon relation satisfies the formula phi with parameter L0 to L minus 1. If and only if the same thing holds in the structure V with A and epsilon relation. Perhaps this looks too restrictive, but actually we can talk about finitely many formulas instead of one single formula, because we can use one parameter as a switch between these finite formulas. I think this is a kind of standard trick in model theory, I guess. Yeah, but in any case, in this way, we see that this principle is equivalent to the following axiom schema, in which I say that for any finite set of concretely given formulas, so also these are objects in metamathematics in the extended language, and for any subset of P omega, there is a transitive set M star such that the same thing happens, and also the equivalence for each formula phi I. Now, this axiom is actually nothing new. It is equivalent to the statement that kappa that the continuum is strictly bigger than kappa. This is easy to see, but I don't know. Perhaps I go into the proof because other proofs are quite similar to this one here. So T0 kappa is equivalent to the statement that kappa is less than, or rather continuum is bigger than kappa. So for direct direction, suppose that this principle T0 kappa holds, and assume that for contradiction that this inequality doesn't hold, meaning that the continuum is less than or equal to kappa. Then let A be a subset of P omega according an enumeration A alpha alpha less than kappa of, sorry, I used wrong P, but I mean the power set. So this is just the enumeration of a power set. A calls the enumeration of power set, and let phi be the formula which capture all the properties I use in the following of the proof, and let M star be the transitive set as in the statement of T0 kappa. And for for this phi. Yeah? So by the choice of phi to be expressive enough, we have that for each alpha, we have that in the model M star, A calls a sequence of reals of length at least alpha. This is one single formula with parameter alpha, so we can manage to express this. And since the property of alpha element of A contains in N, where again alpha and N are parameters in the formula, so it is allowed to use elements of omega 1 as parameters, so I just use them. So this is also coded in an instance of phi. So this means that each A alpha in the sequence is an element of M star. So this means P omega is a subset of omega star, but this is a contradiction because I assume that M star is something which doesn't include P omega. So for the other direction, let phi be an arbitrary formula in the extended language, and let alpha be something bigger than kappa, which for which phi refracts over V alpha. This is just an instance of a Montague-Levy reflection theorem, so we can find such alpha. And then let M star 0 be elementary summary of P alpha, which contains kappa as a subset and A as an element, and so that M star 0 is of cardinality kappa. Okay, downward Leuvenham-Scorn theorem will provide us such an M star 0. But if I take a transitive collapse of M star 0, then this is as desired in the statement of T0 kappa. So this shows the direction from right to left, and this proves the theorem. Now, this statement of T0 kappa can be extended a little bit just to answer the reals problem of reals outside M star. There are several different possible answers, but what I choose here is just to say that there are generic reals outside M star. So phi is again an arbitrary formula in the extended language, and A is subset of P omega, and I choose poset of size less than kappa. So I again use kappa as a parameter in the statement of the principle, and there is a transitive set. So the statement of the principle is that there is a transitive set M star such that kappa is in M star, and there is a poset P prime in M star, which is homomorphic to isomorphic to P, and there is M star P prime generic filter G. I mean generic filter in V, right? So this G guarantees that there is something outside, and in particular, if this is a real, then it's one of the reals which is not captured by M star. And then the same kind of elementarity statement. So as in the other principle, it is easy to see that this principle is equivalent to MA kappa. Just similar. The proof is easy because actually the model M star can be chosen to be of cardinality less than or equal to kappa. So in case of MA kappa, we get almost automatically a generic set. And on the other hand, if we have this one, then it's also easy to see that MA kappa holds. And in that case, this set A can be called the family of dense sets, which will guarantee that the MA kappa will hold. So in particular, if I formulate the statement that T1 kappa holds for all kappa between omega 1 and continuum, then this is just equivalent to Martin's axiom. So far, nothing deep, but if we try to strengthen this principle a little bit, then it becomes more interesting or more complicated. So I like to formulate something similar to the consistent to the version of Takeuti's axiom in 1999 article version, but of course consistent, something consistent, or something whose consistency can be proved. So as the next axiom, I formulate the following. So phi is again a formula in the extended language, and A is subset of P omega. Kappa is again something less than continuum, and some CCC poset of size less than or equal to continuum is given. Then the statement is that there is a transitive set M star such that now the continuum is in M star, and there is a poset P prime, which is isomorphic to P, and M star P prime, generic filter G. But the third statement is a little bit stronger than the other ones, because I choose parameters not only from kappa, but also allowed to use continuum as one of the parameters. So the difference might look quite small, but I can only prove the consistency of this from a rather strong consistency strength. So the theorem I have is that if I assume that DFC plus there exists a Lever-generically superhuge cardinal for CCC posets, then this principle holds. Yeah, first of all, about this Lever-generically superhuge cardinal for CCC posets. So this is a notion I introduced in the joint paper with Andre Rodriguez and Hiroshi Sakaé. This is the second paper of a series of papers, which is still under kind of work in progress. And this is defined as follows. A cardinal mu is Lever-generically supercompact or Lever-generically superhuge for class P of posets if for any lambda bigger than or equal to mu and poset P from this class of posets, there are Q also from the same class of posets, so that P is completely embedded in Q, and there is a VQ generic filter H, and in VH two classes J and M, such that J is elementary embedded into M, and M is inner model of VH. The critical point is mu, and J mu is bigger than lambda, this lambda chosen arbitrarily. And on the other hand, Q is less than or equal to J mu. And P and H are elements of M. And in case of generically supercompactness, I have the condition that J image of lambda is in M. And in case of Lever-generically superhugeness, I even have that J image of J mu is in M. So these are closeness conditions in this context. So with this, I get that T2 holds. Okay, how long may I continue? I don't know.
Oh, this is up to you. I mean, because of my introduction, we started 5 minutes late. So
okay, at least then 5 or 6 minutes more. Okay.
But
yeah.
You see, I mean, we have a long break, so because of that, there is a lot of freedom.
Okay, good. But then something like less than 10 minutes. So perhaps I'll go through the proof. One point, one of the important point is that Lever-generic superhuge cardinal for CCC possessed. Also, sorry. Perhaps I have to mention that I said that in the definition I said Lever-generically superhuge for some class of posets, but in the statement of the theorem, I take the class of all CCC posets, right? But if I assume that there is a lever-genically superhuge cardinal for cis-disciple sets, then it follows that this lever-genic superhuge cardinal is exactly the continuum. So this is the case because, I mean, in the paper, where did I have? In this paper, I defined lever-genically supercompartment slightly weaker without this condition. And just to make the things more simpler, I added this condition, and with this addition, actually we obtain this equality in this case. So mu is just continuum. So so instead of going through the details, perhaps I'll do a picture. How do I do it? Somehow this, no, that doesn't work. Oops. How should I do it? Perhaps I'll go into another. Let's see. Yeah, perhaps I'll draw a. So picture. So we have the situation that we have V, and here we have VH, and we have elementary embedding, and actually H is inside. H is inside M. So we have this to node, and then some structure which is for which the phi is absolute over the structure. But then I'll get something like this one inside, and this is in M because of the closeness of M I mentioned, and H is outside this picture. That's I have this structure, and then I take a transitive collapse of this structure, and then H is still outside of this structure because this has this is isomorphic to the substructure of V, and because of the genericity of H, it must be outside. So we have in M the situation that there's a model for which there's also generic object outside the model. And because of the elementarity, so this is elementary embedding, because the elementarity, I just return to V and say that this situation also happens in V. So this is the very rough picture and idea of the proof. So sorry that I'm so ambiguous, but no, because of the time, I can't say much more about it. Well, actually, I can go one step further and formulate something more similar to the original Takeuti's statement in 1999 article. That's the statement with the parameter alpha 0. And the similar kind of the fake alpha 0 here is this one here. Yeah, perhaps I'll skip the details, but I can prove also the consistency of this. But if I go to I2 lever generically super I2 cardinal, which is just the same kind of lever genericity, but we have for every arbitrarily alpha 0, there is, sorry, for arbitrarily lambda, there is alpha 0 bigger than the lambda, so that alpha 0 is now a fixed point in the elementary embedding, generic elementary embedding, and which is strictly bigger than J of mu. Mu is the lever generically super I2 kind, right? And J alpha 0 is in M. So I still have to fill some details, but I think I can prove the consistency of this principle from IS3. So if I go to this extremely big, large cardinal, then I can also prove something which is more similar to the original Takeuti's assertion. Now, conclusion. So lever generically large cardinals unify strong but natural assertions about the largeness of power set of omega. In the context of a very large continuum. Okay, but this can be expressed with a lever generically large cardinal for CC sets, and we have several theorems which imply this situation. All of these theorems are from the second paper. For example, if mu is just generically supercompact for CC sets, then we know that SCH holds, and there is an omega-1 saturated normal field over P mu kappa for all mu lambda for all lambda. So in particular, mu must be very big. And also, if mu is generically supercompact, sorry, something is missing, sorry. Mu is lever generically. Then for CC sets, then strong form of Martin's axiom holds. So in particular, in our context, the Rees axiom and its dual also holds in this setting, while R less than RJK, okay, sorry, this less than R, just superfluous. LJI holds for any combination of null ideal and mega ideal. Even if we assume to that even label generically super I2, then also Takeuti's axiom or kind of consistent variation of it is integrated into the picture. So with this remark, I just stop my talk. Thank you for your attention.
Okay, thank you very much. Questions, comments?
So I have a question.
Okay.
So perhaps you mentioned it and I missed it, but the consistency of the labor generically super huge.
Yeah.
Can you get that from a super huge?
Yes,
or?
I can get it from super huge. First, I just take care of labor function. Oh, see, I'm not so sure, but super huge. From starting from super huge, you can just add labor function, I guess.
Okay.
Then using this labor function, you just iterate to get a model of Martin's axiom, and that will be it.
Okay.
Okay, I think Lajos has a question.
Yeah.
Yes. Okay, so Sakaé, you mentioned that if you have this axiom R, J, R, then the covering number of I is less or equal than the non-J, and the covering number of J is less or equal than non-I.
Yeah, right.
What about the other direction? Is it true that if the covering number of I is less or equal than non-J, and the covering number of J is than non-I, then R, J, R? True, or you have another example?
I think, let me see. Yeah, I think there is counterexample. I think, but I can't remember it, but I think there is counterexample. Possibly, yeah, I think there is a counterexample, but sorry, so I can't get it from scratch. So I can tell it, but there is some counterexample. Yeah.
Thank you. Thank you.
Okay, Andres has a question, right?
Yes, this is just a kind of general. So, do you know how does this play with all this work by Magidor and Farah and some other people, based on Pitofsky's analysis of the sort of mathematics that goes into from classical formulations of quantum mechanics. So Magidor and it seems to be kind of near, especially, I don't know exactly, I cannot place exactly where, but this seems to be related to what
yeah, it may be the case, yes, yeah, that may be the case, but I don't know the discussion very good, and so I can't say anything, but there might be some connection, right? Yeah, thank you for the comment, yeah.
Okay. Any other questions? Diego.
Yes. I would like to ask perhaps something maybe not that interesting, but I would like to know if something about these axioms like RJI, is known, for example, for a strong null ideal or a strong negative ideal?
Yes,
like
that would be a very interesting question. Yes, yes. You can do similar kind of analysis, but I don't know concretely what happens. But that might be quite an interesting question, I guess. Yes.
Yeah, I think it's interesting to look at. Thank you.
Okay, are there any other questions? I think not. So let us finish this very first session, and let's thank Sakaé again for talking.